All right, so welcome to our first set of flip notes on circuits. Now we've already talked a little bit about electric circuits and how it's essentially just a series of charges flowing around and around. You guys already know that many particles are either positively or negatively charged, but the charge of a particle we refer to as Q, and this is something that we measure in coulombs. So, for example, the charges on protons and electrons, which are the same, protons are positive, electrons are negative, is something called the elementary charge, and it's equal to 1.6 times 10 to the negative 19 coulombs. So, current electricity is all about the flow of charge. And these charges always flow from high to low potential. Just like a ball is going to roll down a hill to an area of lower potential, so are these charges when they flow around. So the number of charges flowing past a point every second is defined as a specific quantity that we call current. Okay, so we can define current, which we call I, as equal to Q, the amount of charge, per time period. And the unit of current is therefore coulombs per second, which we define as something called the ampere, more commonly just called amps, with the symbol A. So to fully understand circuits, we need to talk about two other quantities as well. Those two quantities are voltage and resistance. You'll probably remember a little bit about voltage. Voltage really, if you ever look at any battery, it tells you how many volts the battery gives you. And voltage really is the amount of push or the amount of energy that is causing the charges to flow through the circuit. So it's the amount of energy pushing the electrons. So for example, more volts, more push. The units of voltage are volts, and the symbol for that is capital V. Now resistance is just like it sounds. Resistance is simply how difficult it is to flow through things. Some things are really good conductors, some things are insulators, and the higher the resistance value, the more difficult it is for something to flow through it. And the units for resistance are ohms. And it has this funky symbol that is the Greek letter omega. It kind of looks like a horseshoe. I don't know. So these three things come together in something called Ohm's law, which you probably remember from an earlier grade, which just says that V equals I times R. The voltage applied to a circuit is going to be equal to the current that flows through it multiplied by the resistance. So if we have current flowing through a circuit, then we have light bulbs lighting up, we have motors spinning, that sort of thing. So we're definitely going to be using energy, and so this circuit is using power. Now you remember that power is the amount of energy used per second. And so it's not exactly the same as voltage, it's not exactly the same as energy, but it is related. So power is the amount of energy used per unit time. And we define the power, electrical power that is, as P equal to I times V, which is the current times the voltage. More current flowing, the more power is being used. The higher the voltage, the higher the push on those electrons, the more power is being used. Now if we combine that with Ohm's law that we just learned, we could say, well, remember V equals IR, well I could just substitute this value in here for V, and I would get another formula which says power is I times R, or power is equal to I squared times R. So if I don't know the voltage in the circuit, but instead I know the current and the resistance, I can use this second formula. Another version of Ohm's law would, just to rearrange things, we could say that I equals V over R. And so if we substitute this in here for current instead, we get a third version of our formula which says power is equal to V times V divided by R, which is V squared over R. So any of these three formulas will allow us to calculate the power. It really just depends on what we know about the circuit, whether we know the voltage or the current or the resistance. So here's two examples I want you to try. So just hit pause on the video real quick and see if you can work through these examples, and then hit play to see if you got the right answer. All right, I'm going to assume that you definitely hit pause and didn't just let the video play, and so now you're ready to see how this works. So an electric fan has a resistance of 12 ohms and requires 0.75 amps of current to function properly. How much voltage is required to operate the fan? So voltage is current times resistance. If I need to draw 0.75 amps and the resistance is 12 ohms, then 0.75 times 12 ohms is equal to 9 volts. And that's my answer. And our next question here, an electric heater emits 1.00 times 10 to the 2 watts, or 100 watts. When connected to a 120 volt power line, what is the resistance of the heater? Well, looking at what I know here, I know the power, and I know the voltage, and what I want is a resistance. So looking at my three choices of my formulas, I'm going to choose this third one right here, which says power is equal to voltage squared divided by resistance. And solving for resistance, I get this is equal to voltage squared divided by power, which is equal to 120 volts squared divided by 1 times 10 to the 2, or 100, which gives me a total answer of 144. And the units for resistance, again, are ohms. All right, that's it for circuits.